Chapter 1. Introducing Knowledge Graphs. What are graphs? First off, when we talk about graphs in this context, we're not talking about pie charts or line charts. We're talking about a simple but powerful structure made of two things: nodes, which you can think of as dots or circles, and relationships, the lines connecting the dots. Nodes represent entities, like people, places, or events, while relationships show how these entities are connected. This idea has been around since the 18th century, but has become incredibly useful in modern technology, from modeling everything from social networks to supply chains. The Property Graph Model. This book focuses on a specific type of graph called the labeled property graph. It's popular because it's both flexible and rich in information. Here's what makes it special. Nodes. These are the main objects or entities. They can have labels, e.g., person, product, to define their role in the graph. A node can have multiple labels. They can store data in the form of properties, which are key value pairs, e.g., name, Rosa, age, 64. Relationships. These are the connections between nodes. They always have a type, e.g., friend, lives in, to describe the nature of the connection. They are directed, meaning they have a start node and an end node showing the flow or direction of the relationship. They can also have properties, e.g., since 2020. This model is great because it doesn't force a rigid structure. You can have different properties on different nodes of the same type, which is perfect for messy, real-world data. If you do need to enforce rules, like making sure every person node has a unique ID, you can add constraints where needed. The motivation for knowledge graphs. So why the big buzz around knowledge graphs? Simply put, businesses are overwhelmed with data but struggle to make sense of it. A knowledge graph helps by connecting disparate pieces of data, adding context that makes the information truly useful. Instead of just having a pile of raw data, you have an interconnected web of facts that can be easily explored to find insights, automate processes, and make better predictions. Knowledge graphs, a definition. Not every graph is a knowledge graph. What sets a knowledge graph apart is its organizing principle. This is an extra layer of structure or rules that adds context and allows both humans and machines to understand and reason about the data. It makes the data itself smarter by encoding meaning directly into its structure. This knowledge graph can live in a graph database, be spread across multiple systems, or even act as a logical layer on top of a data lake. The key takeaway is that it's a rich, contextual index over your data that helps you, much like a skilled librarian, find exactly what you need. Chapter 2. Organizing Principles for Building Knowledge Graphs. What is an organizing principle? The secret sauce that turns a regular graph into a powerful knowledge graph is the organizing principle. Think of it as a set of rules or a shared understanding that makes the data smarter and self-explanatory. Instead of having to hard-code business logic into every application that uses the data, you embed that intelligence directly into the graph itself. This promotes reuse and reduces errors. An organizing principle acts like a contract between the data and its users, both human and software, ensuring everyone interprets it the same way. From plain graphs to richer models. Let's look at the different levels of organizing principles you can use. 1. Plain old graphs. This is the most basic form, just nodes and relationships. The meaning is not in the data, but hidden in the code of the applications that use the data. For example, a graph might have nodes P01 and C01 connected. An engineer might know that P means product and C means customer, but a new data scientist would have no idea without being told. This is fragile and hard to maintain. 2. Richer graph models, the property graph. The next step up is the labeled property graph model. Here, nodes have labels, customer, product, and relationships have types, bot. Both can have properties, name, Sophie, price, 9.99. This is a huge improvement because the graph becomes partially self-describing. Visualization tools can automatically color code nodes by their label, and queries can easily find all customer nodes. 3. Knowledge graphs using taxonomies for hierarchy. A property graph is good, but it doesn't capture hierarchical relationships. For example, it doesn't know that wireless earphones is a type of personal audio. To solve this, you can introduce a taxonomy. A taxonomy is a classification scheme that organizes concepts in a hierarchy, like broader than or is a kind of. You model this in the graph using nodes for categories, category, and relationships like subcategory of. This allows for much smarter reasoning. If a specific earphone is out of stock, the system can recommend other products in the same or a parent category. You can even layer multiple taxonomies, like one for product types and another for seasonal promotions, e.g., Black Friday deals. 4. Knowledge graphs using ontologies for complex relationships. For the most sophisticated needs, you can use an ontology. An ontology is like a super taxonomy. It's not limited to simple hierarchical relationships. It lets you define much richer, more complex connections between categories, such as compatible with or depends on. This enables very advanced reasoning. For example, an ontology could define an upsell relationship, allowing the system to recommend an iPhone 12 Pro to a customer looking at an iPhone 12. Ontologies can also act as a semantic bridge to connect and map concepts across different systems in your organization. Which principle should you choose? The key is to practice just enough semantics. Don't try to build a massive, all-encompassing ontology from day one. That's a classic mistake called boiling the ocean. It's slow, expensive, and often outdated by the time it's finished. Instead, start with the simplest organizing principle that solves your immediate problem. Use a property graph if that's all you need. Add a taxonomy when you need to reason about hierarchies. Evolve to an ontology only when your use cases demand that level of complexity. This iterative, agile approach delivers value faster and reduces risk. You can also choose to adopt industry-standard ontologies like FIBO for finance or SNOMED for healthcare to promote interoperability, or create your own if a standard doesn't fit. Chapter 3. Graph Databases. The Cipher Query Language. To interact with a graph database like Neo4j, you'll primarily use a query language called Cipher. Cipher was designed to be intuitive and visual. Its syntax looks a lot like the diagrams you draw on a whiteboard, using parentheses for nodes and arrows for relationships. Nodes are represented with parentheses. A node with a label person and a property name looks like this. P:person with name equals Rosa. The P is a variable to refer to this node later. Relationships are represented with square brackets and arrows, dash parentheses. A complete pattern might look like this. P person minus R lives in dash C. Creating and managing data. Create. This command always creates new nodes and relationships. If you run it twice, you'll get duplicate data. Create. P person with name, Rosa, minus lives in, place, with city, Berlin. Match. This is used to find patterns that already exist in the graph. Match. P person, return P, finds all nodes with the person label. Merge. This is a powerful mix of match and create. It looks for a pattern, and if it finds it, it does nothing. If it doesn't find the entire pattern, it creates it. This is your primary tool for adding data without creating duplicates. To avoid creating duplicate nodes when you only want to add a new relationship, you should merge the nodes separately and then merge the relationship between them. Delete and detach delete. Delete removes nodes and relationships. Detach delete is a handy shortcut that removes a node and all of its associated relationships. To prevent duplicates of key entities, you can create constraints. For example, you can enforce that every place node must have a unique combination of city and country. Querying the graph. Graph local queries. These queries start from a known point in the graph. They are anchored to a specific node or set of nodes. For example, to find out who Rosa's friends of friends are, you'd start your query by matching the Rosa node. Match P person minus friend star 2 F person. The star 2 specifies a path exactly 2 relationships long. You can also specify ranges, like star 1 through 3. Graph global queries. These queries look at the entire graph to find patterns or calculate aggregate statistics. They aren't anchored to a specific starting node. For example, to find out the most popular cities for people to live in, you would match all place nodes and count their incoming lives-in relationships. Match P place minus lives-in dash person. Return P.city count L as population. Order by population descent. Database internals and performance. Graph databases like Neo4j are specifically designed for high-performance traversals, moving from one node to another. They use a technique called index-free adjacency, which means that each node stores direct pointers to its relationships. This makes traversing from one node to its neighbor incredibly fast, regardless of the total size of the database. The speed of a query depends on how much of the graph you explore, not how much data is in the database. This is a key difference from relational databases, which can suffer from join bomb problems on complex recursive queries. With a graph database, deep multi-level queries are what it's built for. Chapter 4. Loading knowledge graph data. When building a knowledge graph, you often need to import large amounts of data from other systems. This chapter covers 3 primary methods for bulk loading data, especially from CSV files, into Neo4j. 1. The Neo4j Data Importer, the visual tool. This is the easiest and most user-friendly way to get started, especially for beginners. The data importer is a graphical tool where you can 1. Draw your model. Visually design your graph model by drawing nodes like person and place and the relationships between them, friend, lives in. 2. Map your files. Upload your CSV files and map the columns to the properties of your nodes and relationships. For relationships, you specify which columns contain the unique IDs of the start and end nodes. 3. Run the import. The tool then automatically generates and runs the necessary cipher scripts to load all the data into a live database. It's a great way to bootstrap your graph, and it even shows you the cipher code it generates, which is a fantastic learning tool. It uses commands like unwind to process CSV rows and merge to load the data efficiently and without duplicates. 2. Load CSV, the cipher command. For more control and for automating imports, you can use the load CSV command directly within Cipher. This is a powerful command that can load data from files on the server's file system or even from URLs like an S3 bucket or a Google Sheet. The basic pattern looks like this. Cipher. Load CSV with headers from file/people.csv as row. Merge p person name row.name. Set p.h equals to integer row.h. Handle data types. Key points for load CSV. It's online, meaning it runs while the database is live and serving queries. For very large files, it's wise to break the import into smaller batches. You can do this using the call brackets in transactions clause, which processes the file in manageable chunks to avoid overwhelming the database. You have full control over the logic, allowing you to handle messy data, normalize values, and build complex graph structures directly from your CSV files. 3. Neo4j Admin Import, the high-speed offline tool. When you need to perform a massive initial import of millions or even billions of records, the fastest method is the Neo4j admin import command line tool. Key characteristics. It's offline. You have to shut down the database to run it. It works by writing directly to the database files, bypassing the transactional engine, which is why it's so incredibly fast, often over 1 million records per second. It's primarily used for the initial bulk load to bootstrap a new knowledge graph. You prepare your data in a specific CSV format. You need separate files for nodes, e.g., peopleheader.csv, peoplepart1.csv, and relationships, friendshipsheader.csv, friendshipspart1.csv. The header files define the columns, including special columns like lock ID person to define unique node IDs, and lock start ID person, lock end ID person to define relationships. The general advice is to start small. Whichever method you choose, test your import with a small, representative sample of your data first to ensure your model and scripts work as expected before kicking off a job that could take hours. Chapter 5: Integrating Knowledge Graphs with Information Systems. A knowledge graph becomes truly powerful when it's integrated with the other information systems in your organization. This creates a data fabric, a unified layer that provides a connected, contextual view of all your enterprise data, no matter where it's stored. The knowledge graph acts as the smart index at the heart of this fabric. This chapter explores the various tools and techniques for achieving this integration. 1. Database drivers, the standard client-server approach. The most common way to connect your application to a knowledge graph is through a database driver. Neo4j provides official drivers for popular languages like Java, Python, JavaScript, .NET, and Go. How it works. Your application code uses the driver to connect to the database over the network. You send Cipher queries and receive results. Best practices. Create only one driver object for your application's lifetime, as they are expensive to set up. Use cheap, short-lived session objects for your queries. Always parameterize your queries to improve performance and prevent injection attacks. 2. Graph federation, composite databases. What if your data is spread across multiple graph databases? Neo4j's composite databases feature allows you to federate them. This means you can create a single, virtual, logical database that queries across multiple physical graph databases without actually moving any data. The consuming application is completely unaware that the data is coming from different sources. This is perfect for scenarios like combining regional sales graphs, EMEA, APAC, with a global product catalog graph. 3. Data virtualization and server-side procedures, APOC. Sometimes you need to connect to data that isn't in a graph. The APOC library is a powerful extension for Neo4j that enables this. Connecting to other databases. APOC has procedures to connect directly to other databases like SQL or MongoDB from within a Cipher query. You can fetch data from a relational table and treat it as virtual nodes in your graph, all at query time. Call apoc.load.jdb. Data virtualization. APOC can create a catalog of virtual resources. You can define a mapping to an external data source like a CSV file, a JSON API, or a relational database table. When you query the knowledge graph, APOC fetches data from these external sources on demand and presents it as virtual nodes and relationships, seamlessly enriching your graph without copying data. 4. Custom functions and procedures. If the built-in procedures aren't enough, you can write your own server-side logic in a JVM language like Java. This allows you to create highly domain-specific functions and procedures that run directly inside the database for maximum performance. 5. Complementary tools and techniques. GraphQL, an API technology that is a natural fit for exposing a knowledge graph to front-end applications. The Neo4j GraphQL library makes it easy to automatically generate a GraphQL API from your graph schema. Kafka Connect, For streaming data, the Neo4j Kafka connector allows your knowledge graph to act as both a source, publishing changes or query results to a Kafka topic, and a sink, ingesting events from Kafka to update the graph in real time. Apache Spark Connector. For large-scale data processing, the Spark connector lets you use your knowledge graph as a data source and sink within Spark jobs. You can read graph data into a Spark data frame for analysis and write the results back to the graph. ETL tools, e.g. Apache Hop. For traditional extract, transform, load (ETL) workflows, tools like Apache Hop provide visual, low-code, no-code environments to orchestrate data flows. They have connectors that make it easy to map data from various sources, databases, files, APIs into your knowledge graph structure. Chapter 6: Enriching Knowledge Graphs with Data Science. Graph data science is all about using graph algorithms to analyze the structure of your knowledge graph and uncover hidden patterns and insights. While the algorithms themselves can be complex, using them is straightforward. Why use graph algorithms? Graph algorithms can reveal things that are nearly impossible to find with simple queries. They can identify the most influential people in a social network, hidden communities of fraudsters, weaknesses in a supply chain, the shortest path through a transportation network. Classes of graph algorithms. Graph algorithms generally fall into a few key categories. Community detection. These algorithms find clusters or communities of densely connected nodes. They are great for tasks like customer segmentation or identifying fraud rings. Examples include Louvain modularity and weakly connected components, WCC. Centrality or influence. These algorithms identify the most important or influential nodes in a graph. For example, PageRank finds nodes that are linked to by other important nodes, while betweenness centrality finds nodes that act as critical bridges connecting different parts of the graph. Pathfinding. These algorithms find the shortest or optimal path between nodes. The most famous is Dijkstra's algorithm. They are essential for logistics, network routing, and recommendation systems. Similarity. These algorithms calculate how similar nodes are based on their properties or their connections. Node similarity is a common algorithm used to find nodes that share many of the same neighbors, which is great for product recommendations. Link prediction. These algorithms predict missing relationships in the graph. They can suggest potential new friends in a social network or products that are frequently bought together. The graph data science workflow in Neo4j. Neo4j's Graph Data Science Library provides a high-performance framework for running these algorithms. The process typically involves 4 steps. 1. Project the graph. You first create an in-memory projection of your knowledge graph. You don't have to use the whole graph. You can select specific node labels, relationship types, and properties that are relevant to your analysis. This projection is stored in a highly optimized format in the GDS graph catalog. 2. Run the algorithm. You then execute an algorithm on this in-memory projection using a simple cipher call procedure. For example, call gds.pagerank.stream my-graph projection. 3. Inspect the results. The results can be handled in a few ways. Stream. The results are streamed back to you in the query response, which is great for exploration. Mutate. The results are written back to the in-memory projection, allowing you to chain algorithms together. Write. The results, e.g. a PageRank score, are written back to the original knowledge graph in Neo4j as a new property on the nodes. This enriches your graph, making the insights permanent and available for future queries. 4. Experiment and productionize. For experimentation, data scientists often use the GDS Python client in a Jupyter notebook, which provides a more familiar, high-level interface. For production, you can set up dedicated secondary servers in a Neo4j cluster to run these computationally intensive algorithms without impacting the performance of your live transactional database. By running these algorithms, you can turn the structural information in your knowledge graph into powerful predictive features that enhance your understanding of the domain. Chapter 7: Graph-Native Machine Learning. This chapter explores the powerful intersection of machine learning, ML, and knowledge graphs. There are two primary ways they work together. 1. In-graph machine learning, using ML techniques to predict how the knowledge graph itself will evolve, such as by adding missing links or classifying nodes. 2. Graph feature engineering, extracting features from the knowledge graph's topology and data to train more powerful external ML models. Topological machine learning, enriching the graph. Graph-native ML capabilities are built directly into the Neo4j Graph Data Science GDS library. This allows you to train models that learn from the graph's structure. A key example is link prediction. While simple algorithms can suggest missing links, a full ML pipeline can provide much more accurate predictions. The process involves 1. Creating a graph projection. Just like with other GDS algorithms, you start by creating an in-memory projection of the data you want to analyze, e.g., a graph of actors who have worked together. 2. Building an ML pipeline. In GDS, you define an ML pipeline step by step using cipher procedures. This involves adding node properties. You create features for the model. A powerful technique is to use node embeddings like FastRP, which are algorithms that encode a node's topological neighborhood into a vector, a list of numbers. This vector becomes a rich feature that captures the node's structural role. Adding link features. You define how to combine the features of two nodes to predict a link between them. For example, you can use the cosine similarity of their embedding vectors. Splitting data. The pipeline automatically splits your data into training and testing sets. Adding a model. You select an ML model to train, such as logistic regression or random forest. 3. Training the model. You run the training process, which uses the features you defined to train the selected model to predict the existence of relationships. GDS can even auto-tune the model's parameters to find the best configuration. 4. Making predictions. Once the model is trained, you can use it to predict new links. You can either stream the predictions back to the user or write the new predicted relationships, e.g., should act with, back into your knowledge graph, permanently enriching it with the model's insights. This entire workflow is managed through a series of declarative cipher calls, which abstracts away much of the complex data engineering typically associated with ML. Graph feature engineering for external models. The topology of a knowledge graph is a source of incredibly valuable features for any ML model. Instead of just using simple properties like age or location, you can generate graph features like centrality scores, PageRank, between the centrality, community IDs from algorithms like Louvain, node embeddings. You can extract these features from your knowledge graph and feed them into external ML platforms like TensorFlow, PyTorch, or cloud services like Vertex AI and SageMaker. By enriching your training data with these structural features, you can often build significantly more accurate predictive models than you could with traditional tabular data alone. In essence, knowledge graphs provide a superior foundation for machine learning by making the context and relationships in your data explicit and computable. Chapter 8: Mapping Data with Metadata Knowledge Graphs. Modern enterprises have data scattered everywhere, in databases, data lakes, applications, and spreadsheets. This makes it incredibly difficult to know what data you have, where it is, how it's used, and whether you can trust it. A metadata knowledge graph is a solution to this problem. It acts as an enterprise-wide map of your entire data landscape. The challenge of distributed data. When data lives in silos, it's hard to get a single, unified view. You end up with duplicate or conflicting information, and data consumers, like analysts and data scientists, waste huge amounts of time just trying to find and understand the data they need. Building a metadata knowledge graph. A metadata knowledge graph captures data about your data. Instead of modeling customers and products, you model the data assets themselves. The key entities in this graph are data platform, the systems where data is stored, e.g., Google BigQuery, PostgreSQL, S3. Dataset, a collection of data like a table, a stream, or a file, e.g., customer_master table. Field, the columns or attributes within a dataset, e.g., customer ID, address. Task and pipeline, the jobs and workflows that process data. A task consumes one dataset and produces another, making data lineage explicit. Data sync, the final consumers of data, such as a BI dashboard or an ML feature set. User, user group, domain, people and teams who own the data and the business domains it belongs to, e.g., corporate sales. Catalog term, concepts from an enterprise ontology or glossary that describe the meaning of the data, e.g., the address field is associated with the location info term. By connecting these nodes with relationships like source, has field, consumes, produces, and owned by, you create a rich, connected map of your data. What you can do with it. Once you have this map, you can answer critical questions that were previously impossible. Data discovery. Find all corporate sales datasets that contain customer location information and are owned by the marketing team. Impact analysis. If this data processing task fails, which dashboards and ML models will be affected? Data lineage or provenance. Where did the data for this financial report originally come from? Governance and compliance. Show me all systems that process personally identifiable information. Connecting data and metadata. You can even take this a step further by connecting your metadata graph directly to your instance data. Imagine a graph with two layers, a bottom layer with your customer and subscription data, and a top layer with the metadata, describing where that data came from and who owns it. An in-data relationship can link the user node in the data layer to the dataset node in the metadata layer. This gives you the power to not only query your data, but also to understand its provenance and quality in the same query. Ultimately, a metadata knowledge graph is a foundational layer for building a robust and trustworthy data ecosystem, enabling self-serve analytics and strong data governance. Chapter 9: Identity Knowledge Graphs. A fundamental challenge in any organization is entity resolution, determining if two or more records from different systems refer to the same real-world thing, whether it's a person, a company, or a product. An identity knowledge graph is a powerful tool for solving this problem. The problem of duplicates. Duplicate data is everywhere. It arises from data integration. A customer exists in your CRM, your billing system, and your marketing platform, but with slightly different details in each. Anonymous activity. A user visits your website multiple times from different devices, leaving behind different cookies and looking like multiple different people. Intentional fraud. A bad actor creates multiple accounts with slight variations in their name or address to abuse a service. The core question is always, do these two records represent the same entity? Graph-based entity resolution, the process. Using a graph to solve this is a three-step process. 1. Data preparation. Load all the records from your various sources into a graph, creating a person node for each record. Harmonize and standardize. Clean up the data. This is a critical step. Make sure dates are in the same format, names are consistently cased, e.g., all lowercase, and extra white spaces trimmed. For example, you might create a new standardized property called m_full name by combining first name and last name fields. 2. Entity matching. This is where you apply your business rules to link the nodes. You connect nodes with relationships like same as or similar. Strong identifiers. First, connect nodes that share a strong identifier, like a passport number or social security number, with a same as relationship. This is an unambiguous match. Weak identifiers. For records without a strong match, look for similarities in weak identifiers like name, date of birth, or address. You can use string similarity algorithms like Jara-Winkler distance to compare names. Connect these potential matches with a similar relationship that has a SIM-score property. Refine the score. You can then adjust the similarity score. For example, if two nodes have similar names but their years of birth are wildly different, you can decrease the score. If their years of birth are also similar, you can increase it. Filter. Finally, remove any similar relationships that have a score below a certain threshold. 3. Create master entities, golden records. At this point, you have a graph where groups of related records are connected. The next step is to find these connected clusters. You use a community detection algorithm like Weakly Connected Components, WCC. The WCC algorithm will assign a unique component ID to every node within a connected cluster. All nodes with the same component ID represent the same real-world person. You can then create a single master entity node, a golden record, for each component and link all the original source records to it. This approach is powerful because it uses not just the properties of the records, but also the structure of their connections to resolve identities, leading to much more accurate results than traditional methods. This is especially true for unstructured data, where you can link products based on the shared words in their descriptions, a task for which graph similarity algorithms are perfectly suited. Chapter 10. Pattern Detection Knowledge Graphs. Once your data is in a knowledge graph, you can mine it for meaningful patterns that reveal insights about your business. This chapter focuses on two powerful use cases: fraud detection and skills matching. Fraud detection. Fraud is a massive problem, and traditional rule-based systems often fall short because fraudsters are constantly changing their tactics. Knowledge graphs are excellent for fraud detection because they make the hidden connections between seemingly unrelated accounts and transactions explicit. The problem. In tabular data, a fraud ring, a group of synthetic identities created by a criminal, can be nearly impossible to spot. The data looks like a series of disconnected, normal-looking customers. The graph solution. When you load this data into a graph, the patterns become clear. You might see multiple person nodes sharing the same address or phone number. While a few people sharing an address might be a normal family, a long, complex chain of people sharing addresses and phone numbers is a huge red flag for a fraud ring. Detecting patterns. 1. Start with an anomaly. You can begin by running a community detection algorithm. If you expect every customer to be in their own separate subgraph, but the algorithm finds large communities with many people linked together, you know something is unusual. 2. Define fraud patterns. You can then write cipher queries to specifically search for known fraudulent patterns, such as match P1 person dash owns or lives at 5 P2 fraud. This query looks for long chains of people connected by shared contact information, which is a strong indicator of a fraud ring. 3. Operationalize. Once a fraudulent transaction is detected on one account in the ring, you can instantly traverse the graph to identify and block all other associated accounts, stopping the fraud in its tracks. Skills matching and organizational planning. Finding the right person with the right skills for a project is a huge challenge in large organizations. A skills knowledge graph can provide a deep, contextual understanding of your workforce's capabilities. Beyond the org chart. A traditional org chart shows the intended structure of the company, but not how work actually gets done. A knowledge graph can model much more. Employee and skill nodes. Project nodes, with relationships showing which employees participated in which projects and which skills each project requires. Data from collaboration platforms like Slack, modeling which employees are discussing which skills to identify true experts. What you can do with it. Find experts. Go beyond simple keyword searches. You can query for people with specific skills and rank them by their total months of experience on relevant projects. Individual career growth. An employee can query the graph to see their own project history. Even better, they can get recommendations for new skills to learn by finding skills that their past collaborators have, but they don't. Build better teams. You can add a social layer to the graph, where employees can rate their experience working with colleagues. This allows you to assemble teams that not only have the right skills, but are also likely to work well together. Predict organizational performance. By analyzing the historical success rates of projects based on the teams and managers involved, you can even use graph-native machine learning to predict the likely outcome of current in-progress projects and identify those at risk of failure early on. In both use cases, the power comes from making the hidden relationships in your data visible and queryable, allowing you to move from simple data points to complex, actionable patterns. Chapter 11: Dependency Knowledge Graphs. Many complex problems, from project management and supply chains to financial ownership and software engineering, can be boiled down to understanding dependencies. A dependency knowledge graph is a model where nodes represent tasks, components or entities, and relationships represent the dependencies between them. Dependencies as a graph. Trying to analyze dependencies in a tabular format, like a spreadsheet with element and depends on columns, is incredibly difficult and inefficient, especially when you need to trace dependencies through multiple levels. SQL is not designed for this kind of recursive path analysis. A graph is a much more natural and powerful way to model this. Each direct dependency becomes a simple depends-on relationship between two nodes. This makes even complex, multi-level dependency chains explicit and easy to query. A query to find if A transitively depends on F is a simple path pattern in Cypher. Match C element ID equals A dash depends on star dash C element ID equals F. Advanced dependency modeling. Real-world dependencies are often more complex than a simple yes-no. Qualified dependencies, you can add properties to the depends-on relationship to qualify the dependency. For example, in a company ownership graph, the relationship can have a part 0.25 property to show that one company owns 25% of another. You can also add temporal properties like from and to dates to model dependencies that are only valid for a certain period. Multidependency. An element often depends on multiple other elements. The meaning of this multidependency is crucial. 1. Additive or aggregate dependencies. Here, the dependencies are active simultaneously and contribute to a whole. For example, a financial portfolio's total value is the sum of its individual asset values. The impact of a failure is proportional to the weight of the failing component. 2. Redundant or protective dependencies. Here, the dependencies provide fault tolerance. Only one is active at a time, and the others are backups. A system will not fail as long as at least one of its redundant dependencies is available. This is common in high-availability software architectures or supply chains with alternative routes. Analyzing the dependency graph. With a rich dependency graph, you can perform sophisticated analysis. 1. Validation. You can easily check the health of your model. 2. No cycles. A dependency graph should be a directed acyclic graph. You can write a simple Cypher query to detect cycles, which represent logical errors. Example, A dash depends on star dash A. 3. Aggregate weights. You can validate that the weights of all additive dependencies for an element sum up to the expected total. Example, 100% ownership. 4. Impact propagation. You can write queries to calculate how the failure of one component will ripple through the system, taking into account the different rules for aggregate and redundant dependencies. Single point of failure, SPOF analysis. A SPOF is a component that, if it fails, will bring down an entire system. In a graph, this is a pattern where multiple, seemingly redundant paths all converge back to a single underlying dependency, e.g., two different virtual servers running on the same physical machine. You can write cipher queries to detect these hidden risks. Root cause analysis. This is the inverse of impact analysis. Given a set of observed failures, symptoms, you can traverse the dependency graph backward to find the common ancestor that is the most likely root cause of all the problems. This is incredibly useful for things like network monitoring, where you want to correlate a storm of alarms down to the single original fault. Chapter 12: Semantic Search and Similarity. A huge amount of the world's data is unstructured text in documents, articles, and reports. Traditional keyword search is often frustratingly literal and misses the user's intent. Semantic search is about searching for things, not strings, understanding the concepts and entities behind the words. Knowledge graphs are the key technology that makes this possible. From strings to things, entity extraction. The first step is to process your documents to extract the important entities. This is done using a natural language processing (NLP) technique called named entity recognition (NER). An NER tool can read a sentence like, "The New York Times is headquartered in New York City," and identify that the first New York refers to an organization and the second refers to a location. The workflow is: 1. Take your collection of documents. 2. Use an NLP library like Hugging Face or the Google Cloud NLP API to extract entities from the text. The NLP tool will return the entity's text, e.g., Patrick Pichette, its type, e.g., person, and often a salient score, how important it is to the document. 3. Store this in a knowledge graph. Create an article node for each document and an entity node for each unique entity found. Connect them with a references relationship that has the salient score as a property. This creates a graph where documents are linked to the entities they mention. Richer search and recommendations. With this graph, your search capabilities become much more powerful. Entity-based search. Instead of searching for the string Neo4j, you can search for the entity Neo4j, type, organization. This is far more precise. Inverse search. You can answer both "What is this document about?" by listing its connected entities and "Which documents mention this entity?" Document similarity for recommendations. You can now recommend similar articles with high precision. Two articles are similar if they share many of the same important entities. You can calculate a similarity score based on the number and salience of shared entities, and even materialize this as a similar to relationship in the graph to make future recommendations lightning fast. The cold start problem. What do you recommend to a new user when you have no information about them? This is the cold start problem. With a knowledge graph, you can recommend articles about currently trending entities, which you can calculate by counting the most frequently referenced entities over a recent time period. Making it truly semantic, the organizing principle. The next level is to resolve ambiguity. NER might extract UK from one document and United Kingdom from another. It knows they are both locations, but not that they are the same location. To solve this, you link the extracted entities to a formal organizing principle, like an ontology or a vocabulary, e.g., Wikidata, DBpedia, or a custom enterprise vocabulary. This process is called entity disambiguation or named entity linking. Modern NLP tools can often do this automatically by providing a link to a Wikipedia page for each entity, which you can then use as a unique key to link to your ontology. Now your graph has 3 layers: the documents, the extracted entities, and the formal concepts from your ontology. This enables true semantic search. A user can search for NoSQL databases and get results for articles that mention Neo4j, because the ontology knows that Neo4j is a type of graph database, which is a type of NoSQL database. You are now navigating the connections between concepts, not just words. This is the same principle that powers modern web search engines. Chapter 13. Talking to your knowledge graph. This chapter explores how to create conversational interfaces for your knowledge graph, allowing users to interact with it using natural language instead of writing code. This involves three main types of interaction between natural language processing, NLP, and knowledge graphs. 1. Natural language as a source of facts, fact extraction. In the previous chapter, we extracted entities to find out what a document was about. We can go a step further and extract facts to understand the relationships between those entities. What it is. Fact extraction is an NLP task that identifies statements in text and structures them as triplets, typically in the form of subject, predicate, object. For example, from the sentence, Pichette is a partner at Innovia Capital, a tool like Diffbot's Natural Language API can extract the fact, Patrick Pichette, employee or member of Innovia Capital. How it's used. You can process a collection of documents and use the extracted facts to populate a knowledge graph. Each fact becomes a relationship between two entity nodes. This creates a rich graph of interconnected knowledge that can directly answer questions like, who works at Innovia Capital, without needing to return the original documents. 2. Using natural language to query a knowledge graph. The goal here is to translate a user's question written in plain English into a structured cipher query that the database can execute. How it works. You can use an NLP library like Spacy and its rule-based matcher. A matcher allows you to define patterns to look for in a sentence. Each pattern is a sequence of tokens described by their attributes, e.g., their text, their part of speech, their lemma. Example pattern. To handle questions like, who directed the Da Vinci Code, you could define a pattern like 1. A token whose lowercase text is who. 2. A token that is a verb whose lemma is one of direct, produce, write. 3. One or more tokens representing the movie title. The workflow. 1. The user asks a question. 2. The matcher finds a matching pattern in the sentence. 3. Your code extracts the key pieces of information, the verb and the movie title. 4. You use a mapping, e.g., the verb direct maps to the directed relationship type in your graph to dynamically construct a cipher query. 5. The cipher query is run against the database, and the result is returned to the user. 3. Generating natural language from a knowledge graph. This is the reverse process, turning the results of a graph query into a human-readable sentence or report. The basic idea. The structure of a graph, subject, relationship, object, maps naturally to the structure of a sentence. A pattern like Euroyacht, officer of, TUC Limited can be easily translated into the sentence, Euroyacht Limited is an officer of TUC Limited. Making it smarter with an ontology. To make this more robust and produce higher quality text, you can annotate your graph's ontology, its schema. For each relationship type, like acted in, you can store natural language templates for both the direct, acted in, and inverse, has in its cast. The workflow. When you want to describe a node, your natural language generation engine can 1. Look up the node in the graph. 2. Traverse its relationships. 3. Find the corresponding templates in the annotated ontology. 4. Use the templates to construct well-formed sentences describing the node's connections. This allows a system to provide conversational answers, generate automated reports, and make the knowledge in the graph accessible to a much wider audience. Chapter 14. From Knowledge Graphs to Knowledge Lakes. This final chapter looks at the future of knowledge graphs and introduces the concept of a knowledge lake. The proliferation of knowledge graphs. As organizations adopt this technology, they often start by building knowledge graphs for specific use cases or departments. Over time, these graphs may be interconnected to solve cross-functional problems. As knowledge graphs become more central to the business, they move further down the technology stack, becoming a foundational layer for other systems. The challenge is that this can lead to a messy, ungovernable collection of many different knowledge graphs. The knowledge lake, a general-purpose foundation. The next evolutionary step is the knowledge lake. A knowledge lake is a large-scale, general-purpose, enterprise-wide knowledge graph. What it is? A knowledge lake is an architectural pattern that sits alongside an enterprise's data lake and data warehouse. It doesn't replace them, it enriches them. How it works? Data can still be poured into a data lake at high volume, where meaning can be figured out later. The knowledge lake is the system that brings meaning to that data after the fact. It stores a curated, interconnected subset of the organization's most valuable data, represented as a graph. The goal: the knowledge lake becomes the primary lens through which business-meaningful data is discovered, consumed, and curated. It's a single, governed, contextualized information system at a massive scale, designed for enterprise-wide reuse. Looking to the future. The core challenge for modern enterprises isn't a lack of data, but a lack of knowledge. We are drowning in information, but starved for knowledge. Knowledge graphs and their future evolution into knowledge lakes represent a powerful opportunity to finally understand and harness the vast amounts of data we collect. By putting data into context, we can move from simply storing information to creating real, actionable knowledge, which is an exciting journey ahead. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.